Okay, so today we're going to continue investigating Chapter 10 and the issue of re-expressing bent or curved scatter plots by applying a variety of transformations. And I'm going to explain a little bit about how to pick those transformations. A lot of it is experiential. In other words, you need more experience to decide. But there's a nice rule of thumb that you can follow, which should give you which kind of re-expression that you want to try first, and then which one you want to try next, and so forth. So the first thing you should have is you should have that handout with 3 examples. There's like a planets example. There's one with a great one from computer science, which is really awesome, I think. All real-world problems that I pulled off the internet from different articles. One was from computer science, one was from biology. And we're going to start with a biology problem today. We're going to look at lobster carapace length, which is like the outer shell on the lobster, and looking at that versus age, something that's a very practical problem for lobster farmers. So you want to enter that data in your calculator. Probably pause the video right now. It's going to take a little bit. Try to be a little bit careful. I wouldn't go too fast. And if you have numbers that are slightly different than mine as you're following along, I wouldn't worry too much. Just focus on the procedures. So first, let's talk about the different kinds of re-expressions that we could apply. What did you guys learn at the end of last week? What are different things you can do to data to try to straighten it out? You can square it. You can logarithm it.
1 over.
You can 1 over it. Put 1 over the data. And you can do a few other things as well, right? You can do that with the x's, you can do that with the y's, either one or both. Those are all things you can try. What I wanted to write down first today is what are the strongest straighteners. In other words, if it's really bent, what do you want to use? And if it's just a little bit bent, what do you want to use? That should give you a rule of thumb of where to start in your problems. So the book has a long discussion of this in Chapter 10. So if you want more detail, go ahead and go there. I don't know if you need it really. You know, if you want a 5 on your exam, that's always a good place to go. Extra is always better. There's this ladder of powers, basically. So let me write down some of the transformations you guys just mentioned. And I'm just going to write them all down in terms of just the response variable, just the y's. Remember, you could also apply these to the x's, and we will be today. So you have y squared, you have the original data. Let's even write that, original data. You can do the square root, that's something no one mentioned. You can take the logarithm. You can go logarithm base 10, you can go logarithm base e, whichever one you want to use. I don't think there's a big difference between whether to use 10 or natural log. They're both good. We're not trying to learn this to a mastery level at this point. But anyway, there's my ladder of possible re-expressions. So which is strongest, which is weakest? The top of the ladder is weakest. As you progress down the ladder, those are going to straighten your data more and more and more. They're going to be the stronger, more straightening types of things. So if your data is really bent, you might want to start out with one of these guys. If your data is kind of moderately bent, you might want to try a logarithm. Logarithms are also kind of science's most popular fix, so a lot of people just go with that a lot of the time and see if it works. If your data is not so bent, you might want to try a square root or even a squared. And you might not want to just try a square root on the response variable. You might want to try it on the x variable as well. Do you have to necessarily use the same kind of re-expression on the x and the y? No. This first example, we're going to do something different to the x and the y. So there's all kinds of possible combinations. I don't expect you to be a master of this. The AP exam doesn't expect you to be a master of this either. Their problems on this are usually pretty easy, actually. The more experience you have, the better you'll get, though. So let's look at a couple examples. So our lobster data, let's scatter plot that up. So you guys have it in your calculator. If you haven't already scatter plotted it, go ahead and do that. So I'm going to take my scatter plot. I've got some stuff in here. Turn my scatter plot on. List 1 and 2, zoom 9. Oh gosh, dang it. Stupid calculator. There we go. Okay, so is it bent? Yeah, clearly bent, right? If we were going to do a 3-feature description, how would we describe this scatter plot? Nonlinear, right? Curved? Pretty strong.
Positive.
I wouldn't say super strong. I'd maybe say like something like moderately strong. And positive, exactly. So, thinking about our ladder of re-expressions, so I've already got one in mind, that we're not going to try everything on this model, it'd take us too long. What do you guys think is a good way to go? Really, really drastic re-expressions, the strongest ones? Really, really weak ones? Moderate ones? How bent is this from the possible regression line? Which the regression line, if you just fit it right now, would do this, right? It'd go like that. Is it really, really bent? I don't think so. I think you either want to try some logarithms to begin with or even something weaker. And it turns out something weaker kind of fits this well. So you guys can see that on your handout, you've already got their re-expression. What re-expression did they pick for this problem that worked well? I pulled this right off an article on the internet, and you guys can see I added some things at the bottom. But I pulled this right off an article on the internet. Square root of y, and they also squared the x's. They did a couple different things. Let's go ahead and do that and see what happens. So we're going to go back to our lists. Square root of y, should we put that in list 3? Sure. I mean, you can do what you want, but figure out something that works for you. Y's usually go like the second thing, right? So square root of y, we're going to go up there and say square root. What's y? List 2. So that should be what you guys see on your paper. If you compare it to what's on your paper. And then we wanted to do x squared, so what should we put here? Oh, 1 squared, you got it. And that should be what you guys see on your paper as well. Looks like it matches to me. So now let's plot this. Now, as you do this, when you're working with re-expressions, I heavily encourage some scratch work. Let's keep track of what our next scatter plot is going to be. What are we going to put here? We're going to put x squared. We're going to put square root of y. Also, put some calculator speak. That will help you a lot. What list is this? List 3. What list is this? List 4. If you write it down, it's highly unlikely you're going to tell your calculator to do the wrong thing. If you don't, it's highly likely you're going to tell your calculator to do the wrong thing. Right? Now it's easy to see. That's what I want to graph. Zoom. Oh man, my zoom doesn't like to work. Zoom 9. Is it straighter? That looks pretty straight to me. We want to investigate a residual plot before we decide is it straight enough, right? That's what you want to do on all your re-expressions. If you do a re-expression and you don't investigate the residual plot, you're like, yeah, that's not good enough at all. So you want to do a residual plot as well. It's looking pretty good though. Let's create the model. So stat, calculate. I did something wrong.
You didn't change the list.
I didn't change the list. This is the original model, which was really wrong, we agreed, right? Shoot. Stat, calculate, x, y. There's the model we want. So let's write that down. So we're going to have, what is the response variable? I'm going to write it down in symbols this time. I'm going to say the square root of y hat, right, equals slope. I'm going to carry this out quite a ways. And not x, but what do? We squared x. And then we've got, oh, and I'm missing something else too. Watch it. That's scientific notation. That's 10 to the negative 5th power, right? So, how many zeros? And I've got a b plus 0.8296. Something like that. You could put carapace length and age in there if you wanted to. I'm not going to overcomplicate this one. Does that make sense to you guys? So we still haven't decided if this model's good enough. R squared says 92% or about 93% of the variation in carapace length is explained by variation in ages. That's awesome. So So that's awesome, but do we have a problem with the residuals? How should we look at that? Let's create our residuals. We don't want the original residuals. We know they're going to be screwed up. We want the residuals of that. So I'm going to want a residual plot that goes, we'll put our residuals in list 5. And then let's compare it to list 1 or list 3. What do you guys think? I think list 3. You can always compare residuals and you'll see problems already in your book. Sometimes they put X on the y-axis. Sometimes they put Y on the y-axis. I like X. It's just simpler. It makes more sense to me. It can be done either way, though. But we don't want list 1 or list 2. We want list 3 or list 4. So how do we get this now? So we've got our model out on the home screen. So we're going to say, I'm going to use the fast way today. Usually we go actual minus predicted. There's a cheating way to do it too, though. It's good to know for times like this. Second list. Do you see something that might be residuals? I do. So I heavily encourage you to do residuals the long way, but when you're in a situation like this where it's a little bit complicated to tell, it's nice to have that fast way to do it as well. So here's our residuals. Let's go plot them. So I've already got it on my paper, so I should know what to plot. Plot list 3 versus my residuals, which are in list 5. Definitely want to zoom that guy over again. And there is my residual plot for the re-expressed model. Does it look okay? It's pretty random. Residual plots don't have to be perfect. You're looking for clear patterns. This is the only thing that concerns me a little bit. Is it has a bit of a fan shape. But see, it kind of comes back down over here a little bit. There's a little bit of random scattering. It's not bad. It's pretty good. In reality, that's often as good as you're going to get. This is real data. So I think we're as good as we can get with this model. It's really nice. Maybe we can find one that was slightly better, but it's pretty good. So we've got up through number 4. We can now use it to predict the age of a lobster if the carapace length is 160. Let's do that. So we'll use our model. Carapace length goes, is it X or Y? I guess I should have labeled this. Y. Y was the, no, I think, yeah, Y is the carapace length, isn't it? Let's double check. Looking back at my data. X is the carapace length. I was talking the whole time like it was the reverse, though. But yeah, it looks like X is the carapace length, and we're trying to see how old they are. So yeah, you can just look back at your data. See, to confirm that, I just went back to my raw data and I saw which number it looked like it was close to. So that's X. So we're going to say, sorry about that, Brandon. You and others. So we're going to say this equals 0.00004629 times 160, right? Plus 0.8296. You always want to ballpark your answers. Once you get it, it should kind of make sense. Let's see. So it says that lobster's about 2 years old. Does that look ballpark for the other data that we have? Questions? I'm leaving something out, right? That doesn't look right at all.
Yeah, you gotta square it.
I gotta square it because I don't want square root of y. I want y. So this is 2.014624 equals square root. So I've got to square both sides, cancel that out. So that squared should give us an answer that makes a little more sense, right? So square it. And I think if you look at your raw data back to your table, you should get that this makes sense. The last question I asked in the handout was what? Is this an extrapolation? John? You said yes. Is it a dangerous extrapolation? You don't think so? Why not? it's not that far outside of the range of stuff we have, right? So it's probably pretty reasonable to expect things aren't going to change that dramatically unless you really know your lobsters and something crazy happens when they get that big, like they explode. I don't think lobsters do that. So I think we're safe. That's probably not a dangerous extrapolation. It's probably a good estimate. So does that make sense? Let's look at another one. Go ahead and flip the page. I'm going to pause this guy. Okay, so our second re-expression example. This should be some familiar data. It's the distance of the 9 planets from the sun and their periods of orbit. I think there's one just like it in your second assignment, as I was just telling everybody else. I would definitely try to get as far as you can on this assignment because it's due Thursday. It's short, but you know, you have to try some different re-expressions. It's not like you're going to pick the right one the first time every time. You got to check residual plots. It takes a little bit of time. So anyway, we first want to get the data for the distances and the periods in our calculator. I've already done that. So here is that data. We're going to change our scatter plot back to 1 and 2 and zoom it. There we go. Description. Form. Not linear. Strength. Really, really strong. Those follow a clear curve. Direction, kind of meaningless, up. Something like that, right? If it's not linear, direction doesn't have as much meaning. So it's not exponential growth, it's maybe exponential decay. Could you model this with an exponential curve? Yeah, sure, but we're doing this a different approach to this class. If you work with exponential curves, you have to learn more math. We're trying to learn less math, so yeah, that's our approach, and our book's approach, which is good. So, think about it though. If I just told you that this is an exponential curve, what kind of re-expression do you want to apply to it? A logarithm. That's the way you want to do it, is with logarithms. We could try logging the y, we could try logging the x. Let's try just logging the y first and see what happens. Okay, so let's just log the y. So I'm going to go and do that transformation, that re-expression. So I'm going to log the y with a natural log. How about that? So I should take the natural log of what if I want to log y? List 2. Okay, and now I should have my scatter plot. Plot what? I guess I should come up here and start looking at it, right? We're going to go list 1, left leave it alone, versus list 3, which is the log of y. See how writing that down really helps. Did that re-expression work? No. Very no. I don't need to look at the residuals. Very curved still. Bad decision. Let's logarithm both, because I think logarithms are the way to go for this one, because the curve looked exponential to me. You might not have enough experience to say that yet. Also, though, when we look at the original plot, was it super bent? Was it just a little bit bent? I think it was kind of in the middle bent, which is another reason to apply logarithms. So we're going to go list, let's go list 3 and list 4. Let's logarithm the x and the y. So I'm going to just start over. Logarithm of the x, logarithm of the y. No. There. And now we'll plot those. Does it look straight now?
Yes.
Yeah, pretty straight. I think that's probably pretty good. We could investigate the residuals. Let's do that. So the residuals, we'll go and we'll do it the fast way. Just check our residuals right here. Have fun, you guys.
See ya.
And let's just compare that to list 1. Or, oh, should I compare it to list 1? We've done a re-expression, so I should compare it to one of the re-expression things. So list 3 or list 4. So let's look at list 5 as our residuals versus list 3. That sounds good. Zoom. Doesn't like to do it for some reason. What? What? it's using the previous model. I need to actually calculate the regression model before the residuals does its thing, because think about what do residuals do. Don't they go the actual minus the predicted? How does it know the predicted? It's going from the previous lobster problem and grabbing the model from that problem. Does that make sense? That's what it has saved in memory. So, you guys see how I figured out the problem really fast, though? It said dimension mismatch, so I knew one of these was not the same size as the other one. That's how I knew. So we need to do this again. I'm going to go stat calculate linear regression with list 3 and list 4, right? There's the new model. We could even write it down. So we're going to have the logarithm of y hat equals 1.49986. No sneaky scientific notation there. Logarithm of x. Any sneaky scientific notation on the next one? Yeah, plus 0.000254. There's the model for log. Now I think our residuals thing should know what to do. So if I'd have done it the long way, you know, the good way of doing residuals, would that have happened to me? No, because I'd have needed the model, and then I'd have been like, oh crap, I need the model, and it wouldn't have happened. So another reason to do it the long way.
Isn't it minus?
Kinsey,
Negative?
did I have a mistake?
I think the 0.002 is supposed to be negative, so I think it's supposed to be subtracted.
Let me look again. Thank you for catching me. There might be a plot point wrong in yours or something. I don't know. Thank you for looking though. Okay, let's see. So I want to do the residual plot. I need the residuals first. I'm going to do it the fast way again. Fast and dirty residuals. Yay! This is ready to go. Not so yay. Because why? It's got a pretty bad residual plot. So, finishing up the problem though, we got our model, right? Forces user model to predict the orbital period for Eris, which is like a thing out in the Kuiper belt. So it's got 1.102 AUs from the sun, so I put 102 where? X. So I'm going to drop 102 right here. Was it 0.5, Brandon? 1.5. Let my logarithm chew on that, so then I'll have the natural log of y hat equals some number. And let's see if my people who've never used logarithms before can tell me. What do I do to both sides to unlock y hat? How do I get rid of that natural log? Oh, you guys have done it before, right? I use exponential base e. That's what cancels out logarithms. I'm not multiplying, I'm exponentialing both sides. There's a button on your calculator for that very thing. So, the prediction we get is 1,032. What are the units on that? Years? Or no?
Earth years.
Earth years, yeah, you're right. Earth years. Got it. So, last question on this problem said, form the residual plot and sketch it. We did that a second ago, right? Got our residual plot still up there. Going back to it. Use this plot to decide if you think your prediction was an under or an over estimate. And also, like, was it a good prediction? Well, the residual plot is like majorly curved, so we should say major caution on the accuracy of this prediction. What do you guys think? Is it an over or an under estimate?
Under.
Why do you think under?
The way that
Yeah, that's really smart. Did they actually give us Eris? Did we have it originally in there? Did they tell us?
560.
Don't they say it in there? Where is it?
I just Googled it.
Oh, you Googled it?
Yeah, sorry.
Yeah, well, it's fine. I think, didn't they have it at the beginning? They said, I thought it was in there somewhere. Kinsey's really right on, though. I was thinking of another way to do it, though. Not following my notes. Oh, yeah. Just think, yeah. This is the way we should think, right? Like, actual minus predicted. So, I know that was a positive residual. Oh, yeah, right here. Where would Eris be? Yeah, this is just what Kinsey said. I'm sorry. I should have just gone with hers. Where would Eris be? That side or that side? That side. It's going to be up here, right? Is this a positive or a negative residual? Don't think hard. It's a positive residual, right? Not a negative residual. Positive residuals. Remember, residual is like if you have a line and you have the actual, the positive residual is going to be that part. So here's the actual, here's the estimate. Is it an over or an underestimate? It's an underestimate. It's actually going to be much farther. It's going to take even longer than we predicted. Does that make sense? Yeah, I should have gotten that, but I'm tired. I should have just listened to Kinsey and had her come write it up on the board. So, you guys get it though? I mean, it's going to be over there. It's clearly positive. Here is the y hat, which is the prediction. It's an underestimate. Nothing really hard. All right, we'll look at one more tomorrow.